So hello everyone, very warm welcome from my side to this fourth tutorial in our tutorial series. And the topic of today is Oasis, and I would like to give you a little bit broader overview or the big picture behind why we would like to connect to and being connecting via a data infrastructure to get rid of our individual research islands and get connected to each other. But as you will see, this has also a lot to do with the aspect of enhancing our research and also how to make our research more sustainable. And sustainability brings me to the first point that I would like to address, which is our publication culture. So what is the physics of today? It's not only a journal, but it's I would like to discuss with you how we're doing research and also how sustainable it is or not. And in that sense, I'd like to introduce my group to you. So you see there are a few group members or some group members, and they all have the individual topics. So they work on their individual workstations, or some of them work on bigger computer clusters or large-scale facilities. Some of them collaborate, so to say, in smaller groups. But at the end of the day, I think what is important in our daily research nowadays is just to publish papers. And so we have published a number of papers, and I just would like to zoom into one of them in order to demonstrate how we're doing research in these days. So what do we find in a paper when you zoom in? So this is a publication on organic halide perovskites. And I'm actually not going to talk about the scientific content. Also, this is an extremely nice research topic, but more about what you can find in the paper. Right? So typically, you would find a table. Yes, we have one. There you see what is the band gap computed with a number of different functionals. A figure also shows this in a pictorial way. And as I said, I can't go into detail what this means. This figure means in terms of research, but you may already see that you see a huge variety of results. So the band gap is much larger or much smaller compared to the experimental range. And this is not only a topic of how we deal with the situation scientifically, but also how we're going to deal with such a situation in terms of data. So I come back to this aspect later on. Just to continue here, of course, we also show a crystal structure in these publications, and typically also we show a few numbers that we have extracted from all the knowledge that we have gained through the years of research spent on such a work. But at the end of the day, we have to say that we never provide all the information in the publication. And I think this has a good reason, because nobody wants to write or read a paper that is 100 pages long or longer. But in essence, it also means that a lot of knowledge that we extract from all our calculations is basically thrown away after some point. So if we summarize what we see there, so we have one publication, we have probably 3 or whatever person years of work that has been dedicated to the investigation. We may have computed or have used millions of CPU core hours in order to produce the data. We may have produced terabytes of data that contain all the knowledge of the quantum mechanical many-body problem that we have solved. And the question is, if we throw all this data away, is it really worth doing the same again and again? So the next student comes doing the same calculation in either the same group or in a different group. So what I really advocate is to not throw this stuff away. I call this residual trash. I will see there will be more trash cans later on, but I really advocate for keeping this data just to be more sustainable. And in order to do so, we started already 10 years ago to develop this materials database, the NOMAD database, novel materials discovery database. And At this point, when we started 10 years ago, we had in mind already to do machine learning on the data together with Matthias Scheffler's group in Berlin. But we realized very quickly that it's not only doing machine learning is a good goal for keeping data, but we were much more organized by having the data in place. Right? So in that sense, we opened up this repository in 2014. And from this point in time on, people from all over the world could contribute to this database and share the data in this public repository. I also have to say that we have more than 100 million calculations by now. These are not only created by individuals who have contributed to the database, but also the data from the big American-based data stores are available in Nomad. So now we have everything still in a centralized facility, so it's not a federated data infrastructure. But in this data store, you can now search and find all the results that have been uploaded to this repository. And just to give you the Nomad repository in a nutshell, because it's a forerunner, I consider it a forerunner of the data infrastructure that we are building now, that we have in mind. And it's fair, already much longer. I said we started in 2012, we made it public in 2014, so long before the term FAIR was coined. But you see from these 4 pictures that this database fulfilled already several years ago the standards of being fair, in the sense that data are findable, so uploaded data, of course, can be found again. They're accessible, of course, because you can only also download the data again, but we made it also human accessible in the way that we created the Nomad Encyclopedia that shows in a pictorial way what people have computed all over the world. Data are interoperable in the sense that in the archive where all these data are stored, you find them normalized and annotated. And finally, the R in FAIR is the reusability, and it's demonstrated by the artificial intelligence toolkit, which was the topic of the last tutorial a few weeks ago. So we have this FAIR database now, and the question is, what do people benefit from sharing their data? And these benefits are manifold, actually. So first of all, sustainability, as you mentioned already, because there is a lot of gain if you don't need to double the work, as said. So if the next student doesn't need to redo the same calculation, but can use the input and output files from other people, be it from the group or somewhere completely different location. So you can reuse and build on other people's work, and by that one can use quite a bit of computing power, or can use the computing power for something that goes substantially beyond what has been done already. As mentioned already, it's also a good incentive for getting organized, because you don't need to bother about or ask the question when a PhD student or a postdoc is leaving, where the data are that the people have created. It also facilitates reproducibility, because you can check other calculations, you can compare with them. And last but not least, it gives your data visibility or results for visibility. So data are becoming citable, so one can get a digital object identifier, and this DOI can be put into a publication. So just to give you an idea how we are doing this, this is my publication list, and here we provide the DOI to the paper, but also a direct link to the data. Or, of course, in addition, we put this direct link as references or somewhere in this paper directly. So you can click on this, and this link would lead you directly to the results. So as you may know already from one of the previous presentations, for instance, the first one, of course, collecting data does not only serve the purpose of getting organized. It's not only a technical issue, but at the end, we would like to use this shared data for enhancing our science, for instance, by artificial intelligence for finding trends and patterns in data. So it's not the topic of the day. I'm not going to talk about this in detail, but I just want to point out here that so far what I've presented all concerns theoretical data. So it's basically the two paradigms, the second and the third, that gives us a handle on performing experimental or computational experiments. But of course, science does not only consist of theory, and that's why we have to listen carefully to Max Planck, who tells us that experiment is the only means of knowledge, and everything else is poetry and imagination. So we have learned now that I'm a poet. This is nice, but I think it's not enough, and we have to go further. We have to go beyond, and this is the reason, or not only reason, but one of the reasons that Nomad is now adding experimental data to its database, and the project behind is FAIRmat. So what is FAIRmat about? FAIRmat is about building tools, easy to use tools, and the data infrastructure. And the purpose is to process data, to store them, to curate them, to share them, and to make them ready for artificial intelligence and for further use. So this is a lot of work, and which is summarized in a very short sentence. So if you like to actually have a more pictorial view of what we have in mind, I can show this picture here. So the idea is that, well, here on the left, you have the scientists, be it from synthesis or experiment or theory, doesn't matter. And these people, they work in the lab, so they work in their island, so to say. And they create the data there. And we should give these people, the scientists, tools such that they can easily process them into databases that may be federated, because I think in particular experimental data are too big to be shipped in a millisecond somewhere else into a database. So data could be localized or could be still local, but the most important point is that these data are shared, and even more important is that the metadata are shared. Because if the metadata, all of this data, the description of all this data goes into a centralized database, then people can look up, they can search for all the results, be it from theory, experiment, synthesis. And what looks here like public viewing means that every researcher, but also people from outside, from industry, whoever is interested in material science data can search for specific materials, for specific properties, and have all this aggregated information in one place. Now, this seems quite a big challenge in view of the fact that we have many different research areas. We have many different sub-communities. We have many different instruments and computational tools. So how would we approach the whole thing? And the idea is to exploit commonalities and synergies. And in this respect, we have identified 5 different topics that are common to all of us. And I just go through them very quickly. So one is metadata ontologies of workflows. Of course, you need to describe all the research data, and this is the fundament of fairness, right? So there's no way out. We are also concerned with the 4V challenges of big data, and I think this hits us all, but all the different methods are concerned differently. Then we need to deal with parsers, normalizers, and converters, because it's very important to not bother the community with new tools and new things that we develop. So these 2 tools that should somehow support the community but not bother them. So if someone loves his or her particular electronic lab notebook, we wouldn't talk people out of this, but rather provide converters that allow to convert the data from one format to the other, from one lab notebook to the other. It's very important to get the community on board, because we don't want to put additional burden on that. Yeah. Data curation, quality assessment is a crucial aspect in terms of interoperability. I mentioned already this example before. How are you dealing with data from different sources that are very different in the results? Yeah, and last but not least, we would like to make data human accessible, and this is why we have built the materials encyclopedia that of course should also be enhanced with experimental data and information about samples and synthesis, but also with artificial intelligence tools that show how one can make use of these data stores in order to learn more from this vast majority of data that we have. So, but very important here is that metadata is something that the community doesn't need to invent themselves, but this is something we have to take care of. And I show you the example going back to the Nomad repository or the Nomad archive, which supports now about 40 or even more community codes. That means we need to understand what the data in these input and output files mean, and we need to bring them into a common format, right? And you wouldn't like to bother the developers with this task, because if you ask how many people or developers are behind the codes, this may be 2 or 3 or 4 in a very big effort, maybe even be only 1. So in that sense, these people, they develop codes because they want to do science. They don't develop codes because they want to bother about data formats or things like that. So it's up to us to take care of the description of data and support the community and the code developers in this respect. And this is the reason why we have written parsers for each of these codes, which at the same time serve as a converter, because internally at least we have to store everything in this in one common format. So we find them now, all this data in the archive, but of course, in order to do so, we need to understand each and every single number in the input and output files, and that's why these metadata are crucially important. So let's now finally go to the project. So how does, or go back to FAIRmat, how do we tackle all these things? Now, you see from this very colorful circle here that we have divided our research and data infrastructure initiative into different areas. So one of them is synthesis, another one experiment, third one is theory. For all this, we build a data infrastructure. We probe them in terms of use cases. We reach out to the community, and of course, we also have to administrate the project. So let me very shortly introduce each of the subjects to you, but putting the focus now again on how to share and what are the challenges in order to get connected to a data infrastructure. And yeah, if you want to read it in a nutshell, I can recommend the paper that just has appeared a few days ago in Nature and describes our efforts. So before getting started with the areas, I like to emphasize that I will again talk a little bit more about recycling, because I think sustainability, as I said, is a big issue, not only in theory, but also in the experimental communities. So, and for this, I've brought not only the trash can that you see on the outermost right that I have described already, but I brought a few more, and you see I'm an expert. I even can already distinguish between different types of trashes. So let me start on the left. This is about the synthesis. So What you see here on the right side, this is a very nice crystal, a perfect crystal of aluminium nitride provided by Martin Albrecht from the Institute for Kristallzucht. And I think this is a crystal that everyone would like to have, because you would like to show very nice measurements on a perfect crystal. But what I would emphasize here is, even if this is a perfect crystal, typically the recipe behind the crystal growth is not published. And this is basically one of the major issues here, that there is no comprehensive source of synthesis relevance data on materials. And there are several reasons for this. One, of course, is that probably people don't want to share their secrets, because they want to keep the competitive advantage. If you grow the best crystal on this planet, why should other people do the same? You want to publish nice papers with this. So, and this is particularly relevant in the industrial environment. Of course, they wouldn't share everything. So it's understandable from a human point of view, right? But there are also other reasons why very often this information is not published, because very often the metadata are not complete and are probably only written down in notes, in handwritten notes, or just exchanged information at the coffee break at the conference. Right? But I think even if everything is published about this crystal, if we only provide or publish success stories, it leads to bias. So in other words, probably the synthesis recipes of these crystals will never be published, because they're not so beautiful as the others. And I think there we have also to rethink our publication culture, because publishing only success story leads to bias. So we need to publish also failures, otherwise we will never find out why something does not work. So publishing success stories tells us why things work, but we also need to know why other recipes, for instance, don't work. So also publishing failures enhances our understanding, but it's not very popular so far. So, and this brings me to our area A, synthesis, that tackles reproducible growth for materials from these 4 different routes that I show you on the right here. There will also be a reference database for crystal growth, but most important, talking about islands and talking about how to bring together the community, we have in mind to harmonize the metadata schemas of synthesis and experimental characterization, because finally, if you publish your data, you want not only to know what the experimental characterization technique was about, but also what the crystal is about that has been characterized. And very similar, we also want to bring together the knowledge about computational approaches to synthesis with the actual synthesis growth. So this brings me to the next type of trash, actually, and these are metadata. So, and with this, I proceed to area B, which is about experiment. And yeah, maybe you know, you're the expert already, and you know that we are starting our experimental, let's say, initiatives with 5 very different experimental probes that give information about different properties of the sample, be it a structure like an electron microscopy or electronic structure, like in angle resolved photo emission. So we start with 5 experimental techniques, which are very different because each of them has the specific challenges regarding 4V and processing and storage and things like that. But I like to point out 2 of the main goals here. And one is, of course, to come up with the proper metadata and workflows for these very extremely diverse characterization methods that are used by the community. But also that we want to provide to the community tools that allow them to extract, for instance, this metadata automatically, for instance, through electronic lab notebooks, and to provide the community also with laboratory information management systems. So talking about lab notebooks, let me just point out the, let's say, heterogeneity that we're also facing here. So I mentioned before that there are many different solutions on the market, and people either love one or the other. And this could be so even for one type of instrument. So if I take, let's say, a microscope here, and one community is using a microscope number X, and another one called Z, and then another big lab Y, and another one creates this own lab notebook. So how can we deal with this situation? So because in one case, for instance, the vendor provides it. In the other case, the institution has bought a solution. In the third case, people prefer an open access solution. Or in the third case, it's a homemade solution, or whatever you can think of. So of course, internally, we have to decide on one format, on one solution. But if we now think about harmonizing the whole thing, and let's unify, and we take yet another one, which is called electronic lab notebook number F, like FAIRmat, then of course, people who use this already will be happy, but you will somehow shy away everyone else, because they will be very, very sad, because they don't want to change. So in that sense, I like to get back to the slides that I've shown you before. So I emphasized before that it's important that metadata, ontologies, workflows are provided by us who create the data infrastructure, but it's equally important also for the experimental community. So it's also parsers, normalizers, and converters have to be provided by us in order to keep the community on board. So it's up to us to provide these tools. Now, but experimental characterization also comes with other challenges, and these are lost metadata. Well, I call it like this. Think about if you go to a lab, then take a measurement. Very often people write down some notes on just a piece of paper. The same may be true for the synthesis of a sample, or for the setup of a technique, of an instrument. But then maybe when measuring something, you also take additional notes that you throw away afterwards. But at the end of the day, like mentioned before, it's important to publish a paper, and very, very often, even if the data are kept, all this additional information that has been taken on the way of creating the data is just removed. So again, we need to ask the question whether data that are not well annotated are worth being kept. I think there are many data around on this planet. They are kept for the sake of being kept, but they are not well described. So at the end, we cannot use them because we don't know what was behind when they were created. So that annotation and metadata are important is also important in view of interpreting our results. And here I would like to briefly address the challenge of heterogeneity of data, in particular variety and veracity. So these are two of these 4V of big data. So what you see on the right here is the optical spectra of silver, right? So in the best possible world, you would argue they all should be completely identical, because silver is a noble metal, a very nice material, a very simple material, just an elemental solid. And optical spectra is a pretty simple two-dimensional plot. But I mean, if you just look at this without going into details, you see we are not in the best possible world. There's a lot of differences, and they have different sources. So one, of course, obviously, it also tells us that the sample quality is important, because there may be contamination in the sample, there may be surface effect or whatever, right? But another problem is that there are many ways of measuring the same property. So it's nice in terms of physics, of the variety that we have, but it's not easy to understand, to describe in terms of data. So for instance, to get this dielectric function, we may use ellipsometry or absorption or reflectance spectroscopy, also electron microscopy or spectroscopy. So interestingly, of course, none of these techniques gives you this property directly. There's always a transformation step behind, and maybe even models to interpret the data, which again somehow adds not only variety but also veracity to the data. And needless to say that there are many instruments and data formats available on the market. Yeah, but in addition, of course, we also can compute the same quantity, and there are also very many different ways of computing the same quantity. So it's quite obvious that there will be a variety of techniques giving the same thing, and the veracity is a real big challenge here. So to get rid of this veracity, or at least to understand better what we're doing when looking at data, of course, metadata play a crucial role here in order to assess the data quality. So it's facilitated, but it's not the only thing, because we also need to know what is the best possible data that we can achieve. So benchmarks are urgently needed for all kinds of properties and all kinds of materials. Yeah, but we also need to develop metrics that allow us to measure the differences and to measure the deviation from the ideal result. So otherwise we don't know how much influence a certain contamination of a sample has, or how much influence the parameters used in the calculation will have on the results, or the computational technique on the results. So in that sense, I just would like to give you a snapshot of something that we have very recently developed and are to some extent also implemented. This is a similarity matrix based, matrix based on a metric, the similarity matrix. And this allows it to compare basically, so the numbers go from 0 to 1, but this allows it to compare how close or how far away one data set may be to another. So this is just getting started, but I think for a fair database, this is crucially important to think about data quality assessment. Yeah, let me very briefly also show you another, get back to the residual trash can that we have looked up already later, because it directly gets us to area C. I've shown you the example of area C to theory. So if you now consider that the whole endeavor that we have in front of us, so we just started, is that huge that you see that the fair data infrastructure, fair data infrastructure is a little tiny little detail, or tiny little aspects of everything. And even within theory, it's only a small part of what we have in mind, because there are many different methods to compute things, to simulate things. So far, the Nomad repository basically captures theory data from density functional theory. So there are classical simulations that come with a lot of volume. They are very subtle, quantum mechanical many-body techniques to describe excitations, for instance. And so everything comes with its intricate subtleties. So what we have in mind here is to, first of all, enhance the services like the encyclopedia and the AI tools, but in particular implement many more calculation techniques, computational techniques into the data infrastructure. And this somehow connects also to my last type of trash cans, which are candidate materials, because I think there are many high throughput initiatives that have been started many years ago, actually, to compute a lot of data, but you can of course also do this in terms of experiment. But for the sake of simplicity, let's think that we would like to have a material fulfilling 5 properties, and you compute these properties. And you compute these properties for many materials, and you just see whether all these criteria are fulfilled by the materials that you look at. So at the end of the day, you may find out that there are only 3, but you have investigated 13,000 of materials in view of the applicability to a certain application. So that means that the 3, of course, are kept, but for the others, we typically close the lid, and these, the 3 basically go to heaven, the others go to hell. So, of course, it's needless to ask the question whether it's trash. Of course, it's not, because I think all these calculations we have been performed are probably very valid, not for the purpose we have been looking at them, but for a different purpose. So again, I'm advocating for recycling, and of course, a data infrastructure helps us to store all this information, even if it's not relevant for the purpose-oriented research. So now we have, in order to get sustainable, we would recycle everything that it's not used in publication, but it's valuable information. We would recycle all the candidate materials that could be used for another purpose. We recycle all the metadata in order to describe our data well. We also recycle unsuccessful synthesis recipes to learn also from failures. And if we have this, actually, then we are ready for really harvesting all this information that we have. And yeah, we can make a gold mine out of this. And very important, we should get away from the silos, because by sharing data, of course, we can also share the gold mine and share the gain that we have. I mean, now we make gold out of it, and the question is, of course, how? Now, and this brings me back to our data infrastructure, because a prerequisite for really harvesting all this information and this treasure means that we need a digital infrastructure that allows us for doing so. And in FAIRmat, this is area D that builds a federated infrastructure, and this is very important. So even if data are kept at the place where they are created, and this is inevitable for many techniques and labs, this still could be a federated data infrastructure, in the sense that the different bits and parts are getting connected to each other. So I already mentioned the metadata should be centralized, such that we allow to search for everything at the same time. We need to take care of user management systems. We need to take care of security. We need to take care of curation, data quality assessment, and things like that. We will create a portal that allows then for this, what I call sloppily public viewing. And an important aspect of this is what we call the oasis. And this is the whole today's workshop is about, and you will know much more about it after Markus' talk, and also when he and his team is presenting what the reasoning behind oasis is, and what the purposes are it serves. So in short, the oasis is basically the same infrastructure that we have developed already, but it's a standalone version of it, such that it can be used in different labs for managing individual data. And of course, you may ask the question now whether we are going back to our silos and islands. No, yes, we can create our islands, but we need to make sure that these islands are finally connected. So an oasis is an infrastructure that helps preparing the data to sharing, for instance, within a lab or within a research group. But the purpose, of course, is to be a building block of a federated data infrastructure. And so, for instance, a good application of such a oasis could be any case of a use case demonstrator, where people from different areas get together in order to demonstrate or see how the tools that we develop in FAIRmat enhance the life and daily life of scientists, and are at the end useful. So they also provide us feedback whether what we develop is useful for them. And of course, use case demonstrators are always good to connect different subgroups and research fields, and also to other NFTI consortia, to other projects. And for this reason, or one of these reasons, it's one of the reasons why also outreach is a very important aspect. So first of all, to inform the community, and but also to support the community with the tools that we are doing. And so in a nutshell, We organize, for instance, the tutorials that we are having today, or also hackathons and workshops and international conferences to inform and exchange with the international community. Of course, then we also have to somehow to get the community on board. So I think it's probably more easy to get the postdocs and students on board because they immediately see the need and also the benefit of tools that we develop. But of course, we also have to somehow to convince the decision makers that this will be data infrastructure will enhance the future research. Yeah. And last but not least, of course, we also need to make sure that all the knowledge on data and data infrastructures enter the curricula in the community, in the universities, and this we do jointly, for instance, with the German Physical Society. So, at the end, let me also talk 2 minutes about administration and the coordination. It's not to talk about the administration itself, but I would like to point out that we have created a data center. We call this the FAIRmat headquarter or hub, which is located here in Berlin at the Humboldt University. And the reason is not to create yet another island of people working on the data infrastructure, but it's more to exploit the synergies, because we have entered completely fresh no man's land in many aspects of data handling. And so we need to bring together people with different skill sets, and this is most efficiently done if you combine them in a hub, in a think tank to exploit the cells. But of course, it's not, the purpose is not to create yet another island, and that's why I also would like to show you who is behind the whole project. These are nearly 60 PIs from all over Germany that are behind this, and they're very effectively working together in order to make all this happen. But again, talking about islands and talking about connections, of course, also physics and material science and is not an island by itself. So there are also communities that share some of the aspects with us. So for instance, here I list the NFTI consortia that are related, somehow related to materials science or are inside material science. But of course, we also share commonalities with other consortia by mathematics or physics. And again, even the NFTI is not an island, because we need to connect ourselves to European-like initiatives and communities, establish collaborations with other countries, not being restricted, of course, to Europe, but also to the whole community, the world. And probably some of you have listened to Jim Warren's talk last week, who is one of the NIST directors for the data management there. So, and this brings me to the end. I would like to somehow advocate for enjoying our islands. I think we can enjoy the research in our islands, in our oases, to somehow prepare the data in our oases, even to harvest fruits in our oases and islands. But we shouldn't forget to connect all them. There's always ways to do so. You can take a camel, ride a horse, you can ride a car, you can take a highway, you can take a wireless connection like a boat or a plane. But most important is to stay connected in order to serve the purpose of a shared infrastructure for bringing the community together. And with this, I would like to thank you for your attention.
Okay, thank you very much, Claudia. I think we have room for a few questions. I think we can take a few minutes. So if you have questions, please just raise your hand, or you can also put them into the chat. So let's give people a few seconds to make up their minds and type a question. Maybe I can ask a question first to get the discussion started a bit. You were mentioning a lot that this is like quite an effort, right? What we want to have, and that this data sharing isn't coming from alone. People actually have to participate in this, and we are trying to build all this infrastructure to make it possible. How do you think can we incentivize people to actually use our infrastructure and really be part of it? I mean, just convincing people that this is a good idea is like one thing, but really in the end, they have to make some efforts, right, to describe the data and to put in all the metadata that is necessary. And how do we do that?
I mean, what I meant or already said is I think we need to provide the tools. So we should bother people that they have to change their formats. They have, of course, they have to change their way of doing research in some way to adopt the tools. But at the end, the tools must be so comfortable and convenient for them such that they somehow make life easier and not harder. And the other thing, that's why I put already the benefits there. So I see it in my own group. Of course, it took a while until people understood in my own group what the whole thing is about. But I see now, if they create a crystal structure or an input file, they go to the normal repository and see if they find something similar. Or they take a calculation and, for instance, you can double or quadruple the unit cell size in order to put a defect in it, but you don't need to do the single calculation anymore. So, or can use the input file from that. I think people are once they start using it, they see much more the benefits. And so, of course, spread the rumor, invite them to hackathons. Particularly, I think the young generation is pretty open to all this. I'm pretty confident that it works. In particular, having these nice tools that you and your team are creating. So.
We have one question from the audience from Sasha Clavon. I'm not sure if you can unmute yourself or if I have to do it.
I can.
Okay.
Yeah. Okay, so I'm absolutely for reusing the data and making it accessible for everyone. And one thing I'm still wondering about is how do you plan to cope with identical or near identical data? Because on the one hand, sorry?
Yeah.
Because on the one hand, you of course would like to have, for example, confirmation, so veracity, that a recipe, for example, a synthesis recipe works by having others repeat it and promote or telling of their success. But on the other hand, for let's say you want to have some machine learning AI go through the data and learn from that, you don't want all the duplicates to have a higher weight. Or maybe in some sense you want, but not for everything.
Yeah, I think in some sense you want, right? So
in some sense, yes.
If the same group is uploading the data twice, the repository will tell you you have uploaded already. So this cannot happen. But for instance, having the same calculation done with even with the same functionals from different groups, or the same experiment carried out in different labs with different samples and different machines or so, this also could give you already feedback about the data quality or the sample quality or so.
Right.
So, but of course, if you do machine learning, you might filter your data and just allow one calculation of the same kind inside. Probably then you have to mark the one you trust most, right? Or which is more compatible with other data. So I think there's a lot of intricacies, because I mean you have calculations with different functionals, then you know one function is better than the other, but probably one of the calculations has better computational parameters. So which one do you trust? I think
that's my
there's
question.
A lot of other questions you have to ask in addition to this, but it's definitely a very, very valid aspect. Yeah. But in the repository, I think it's good to have as many as we have. So for instance, we have now compared 800 calculations of aluminum density of states. It's very interesting to see the patterns that you find in these calculations. So it's, even from a machine learning point of view, it's very interesting to explore the data space itself, even if it's seemingly the same data.
Yeah, definitely.
And maybe if I might add a little comment to that, it's like having the metadata allows all these kind of choices to be made, right? To see, is this identical enough for me? Would I ignore this if I already knew this, or is this different enough for me to consider for certain things? And the same that you're saying about similarity, you can also, or equality, you can also say about quality, right? Whether your calculation is good enough for your KI, for example, to train and stuff like this. So the availability of the metadata at least enables the people to do these kind of things. There is a question in the chat. FAIRmat, is its ultimate goal of evolving one point source of reviewing the selected research data?
Well, of course, when can you say, I don't know if I understand the question right, but of course you can also use a repository for reviewing publications and the particular publications about data. So for instance, we had this already. There is the Nature Scientific Data, where the reviewers want to see the data sets. And then you probably, if you keep the data secret up to publication, we can provide a key to the referees. They may see the data, then they review the data, and at a certain point the data should be public at the end. But for the reviewing process, we can do that.
If we interpret the question beyond publication and just seeing as like, is the goal to have like the one source that people go to find data when they're interested in material science or in solid state physics or whatever subdomain of material science?
Yeah, okay. I mean, so far, at least for computational material science, NOMAD is the largest data store on the planet. Not only, as I said, because people from all over the world have contributed individual calculations, but because we also provide the raw data from AFlow, from Matthias Project and OQMD. So in that sense, it already combines several databases. And so I think it definitely is a good place for searching for materials. Of course, this is a very big field and many initiatives are coming up, but so far I see that probably we are at the moment the biggest one of its kind.
So I don't see any raised hands anymore. Let's thank Claudia again, give one more round of virtual applause, I guess. And then we could jump to the next point of this tutorial.